All right, hello everybody. Let's see. So last week the activities were not planned well by me. I apologize for that. So we didn't really get a chance to review any of the answers. So I wanted to create a video where I review the answers, so you have that opportunity to get any kind of feedback that you would like. So let's go ahead and dive right into week four, activity two. So the first question was this hypothesis of the study? What was the hypothesis of the study reported, and did the raw percentages align with the hypothesis? And I think most people nailed it here. So the idea was that it was the extended antibiotic prophylaxis would reduce the incidence of infection postoperative complications. Um, and the raw percentages did not align with the hypothesis. So good on that one. We have learned that not significant does not mean no effect. Given this, many statisticians are uneasy with the way the sentence below might be worded. So remember, they said in their abstract that extended postoperative antibacterial prophylaxis for patients undergoing elective thoracic surgery requiring tube, this I don't know, thoracostomy. I don't know what that is. Forgive me. Did not reduce the number of infections complications compared to preoperative. So this idea was that it did not reduce. Um, so um, what can we do to say to do it better? So I like this one. It showed that the key here, I like this, it said extended postoperative antibacterial prophylaxis for patients undergoing elective thoracic surgery requiring tube. Yeah, showed no statistically significant reduction in the number of infection complications compared to the preoperative prophylaxis. So we can't rule out that it doesn't reduce it. Uh, all we do is we fail to reject the null, right? And so I think this is appropriate that just in this we didn't find statistical evidence of it, even if we can't rule it out and prove definitively that it doesn't reduce the number of infections. Okay, and so then I had you read a abstract about common effect sizes in uh, social psychology. Remember that there are some guidelines that like small is zero point 0.2, medium is zero point 0.5, and large is zero point 0.8 standard deviations. But in psychology, the Cohen's d uh, uh, values would be something like 0.15, 0.36, and 0.65. So obviously smaller. So people said yes, Cohen's d traditional guidelines tend to overestimate what constitutes small, medium, and large in the context of social psychology research, right? That might not be true in another discipline, but we have to always take into account what's the research context. If you were to um, look instead at like audiology, so that was the next question. Um, you would find that the Cohen's d or Hedges g, which is basically a Cohen's d, of 0.25, zero point 0.5, and 0.93. Um, so these are larger than the actual guidelines. That you actually find stronger effects in speech language pathology, typically in research than you do in social psychology. So everything is relative to the discipline that you are actually um, studying. And then I asked you to check all that apply. If you're doing an audiology study, um, which one is true? So the first was, does Cohen's d effect size in audiology and speech language pathology are roughly double the effect sizes in social psychology? So this was like 0.15 to 0.25, 0.36 0.36 to 0.55, so not quite double, um, but uh, but definitely larger. If you were a content expert in social psychology, you would expect that a statistician will recommend a sample size that is twice as large as a typical sample size required in a subject matter expertise and as a subject matter expert in ideology. So the idea is that if you double the effect size, do you need to double the sample size? Um, and the answer is no. You would actually need to do it 4 times as large if it was double the sample size, but it's not here. So in other words, let's see here. So it would be, in fact, we could do this a little bit more cogently. So if we did, let's just do a typical effect size of at the 50th percentile. So in psychology, it's 0.36, and in ideology, it's 0.55. So let's do this. So we have 0.36, and then we have 0.55. So this is equal to, let's look. Let me get a calculator. 0.55 divided by 0.36. That's equal to 1.52. And then I'm going to square that value times 2. So I would need approximately 3 times the sample size in psychology as ideology. And of course, Cohen's d effect size does need to be interpreted with respect to the domain. So everybody got that. Okay. All right. So big thing here is that as your effect size goes down, your sample size isn't following a linear decrease down or a concomitant down. It's going to increase by the square. And so just be mindful when you're doing power analyses for your own work that a small reduction in sample size or in effect size can have a large impact on sample size. Okay. All right. So now let's go ahead and look at activity 3. All right. So what I wanted to do first was to look at whether or not we could replicate this power analysis. So I'm going to put this over here. So what did we have? We had a Cohen's d of 0.65. So all I have to do is 0.65, a standard deviation of 1, and two-sided two-test, and 0.8. And so this would be a sample size of 39. The next one, what would be the problem with using effect sizes even from published meta-analyses to plan a sample size? So what is that problem? And it seems like people said in general, publication bias leads to higher probability of statistically significant or larger effects. Yep, resulting in an overestimate of the true effect size. I like this. Effect sizes from meta-analyses may not account for context-specific factors of the population. And that's definitely true that you're trying to study, that you're specifically trying to study. So it may not account for study heterogeneity and temporal changes. So I like that as well. Again, you do want some empirical basis of what effect size that you are actually studying, but even if you find a good meta-analysis, everything has to be interpreted within context, which makes it difficult. And you're fighting publication bias, potential publication bias. So in fact, I gave you an example of this publication bias. So the study by Yang et al. Published showed that studies in ecology and evolutionary biology may exhibit as high as a four-fold exaggeration of effect sizes due to publication bias. And so if you were a statistician preparing for a grant, what sample size would you actually recommend? So this was continuing along this idea that they needed 39 with an effect size of 0.65. So a lot of people said, okay, let me divide the Cohen's d by 4, And I think that's a reasonable thing to do. So I'm going to divide the Cohen's d by 4. And what would I get if I did that? Let's see. So if I were to do uh, d divided, or 0.6d equal to 0.65 divided by 4, and I would get 0.65 divided by 4 is 0.1625. Okay. And so now um, the question is, um, what sample size would I recommend? Well, now I'm just going to, instead of 0.65, I'm going to put 1.625. And so I don't expect the sample size to increase by 4. I expect it to increase by quite a bit more. In fact, now it's at 596. So I would say that we would need 596 per group, or if you're doing two different groups, that would be 596 times 2. Let's see, so that would be, so 600 times 2, 1192. Is that right? I think that is right. Let me double check. 596 times 2, 1192. Perfect. Okay. So then the last one, let's see. So the median factor at 0.5. Okay, so this person's doing a 0.125. The only thing I would say with the standard deviation is when we're talking Cohen's d, the standard deviation is always 1. So if you did 1.125, you'd have to do a standard deviation of 1, and it'd be 1,031. But you can see that's much larger than the 596. Just going from 0.1625 to 0.1235 made a huge difference in going from, it over doubled the sample size. So got to be very careful about that. Okay. Um, so now use a sample size calculator to replicate this. Let's see here. What was this one? Oh, wait. Do we have. Okay. Okay. Let's see. Do we. Oh, use. Paste the result. Okay, I see here. Okay, some people got like 4264. And then some people didn't get this here. So is this scenario 2? Oh yeah, scenario 2 continued. Okay. Alright. Oh wait, where am I at? Okay, so scenario 2. Got it here. Okay. We will, sorry about that. I was confused of what was lining up with what. So, assuming full retention at 18-month follow-up, full compliance with the intervention protocol, and population standard deviation of 0.80 percentage points, we will enroll 84 participants, 42 per group, diagnosed with prediabetes to detect a clinical and meaningful HB1C mean reduction of 0.5 percentage points with 80% power at 0.05. So let's see if we can replicate this. So the population standard deviation is 0.8, and we want a mean difference. What's meaningful is, let's see, reduction of 0.5 percentage points. So I'm going to put 0.5 here, and I get a group is 42. Are there any assumptions that the authors are making that may concern you? So let's see what people said. Oops. Nope. That's not what I wanted to do. Let's see what the authors might have said here. Yeah, so they assume 100% retention and full compliance, which is considered unrealistic. Lower than 100% retention reduces the sample size. I definitely agree. Assuming a standard deviation of 0.8 is concerning. If the standard deviation is larger, the study may be underpowered. That's definitely true. So it's very common to use other people's standard deviation, which may not apply to your specific population. And again, assuming 100% retention, full compliance is really a big deal. Okay. In fact, some evidence you might consider is that the in an app-based intervention, which is what this was, or something that requires people to change their behaviors, the median attrition rate is 40%, according to one study. And even in clinical trials, um, a dropout rate of 15 and 40% are very common. And even in the best studies, the ones that get published in top medical journals, um, 20% or more, um, they found 20% or more dropout in 18% of RCTs, right? So this idea is that if you're likely to have attrition and dropout. And so what might you ask the person to do? I would say assume a dropout rate of up to 40%, around 20% or more dropout. Also consider, oh, I think people ran out of time, but yes, you need to somehow increase your sample size to account for the actual attrition. And that's so, as you can see, like when you start considering what is it a realistic effect size versus what is an optimistic effect size, and what's realistic in terms of dropout and attrition versus our goal of having a complete compliant and study. Our sample sizes just get bigger and bigger and bigger. So I think that really covers most of it. Um, the only other thing, this last question, which nobody got to, was this idea that they studied and they got an answer to their research question, and that's what the study was powered on. Um, And so what as a statistician, the scenario that I created for you was you did this power analysis. It was powered on that one research question, but now there were secondary research questions that the authors decided to answer after they've looked at the data. And so they come back to you with the sentence that on average the HbA1c values decreased by 7.3% with a p-value of 0.41. And so follow-up analysis revealed that participants assigned to intervention were less likely to meet clinical screening thresholds for anxiety. So like 0.56 is the risk ratio, and depression. And together, the evidence suggests that the mobile health app improves aspects of both physical and emotional well-being. And so the issue is that they did these additional comparisons. Those weren't included in the power analyses, so we didn't have the opportunity to adjust for multiple comparisons. So as a statistician, I would have to tell you we would need to adjust for these multiple comparisons. All of these uh, these tests for multiple comparisons, which would likely make them not significant. So the idea is if you do have secondary research questions, please, please, please know ahead of time, because when you adjust for multiple comparisons, your sample size is going to need to go up even more to account for the fact that your family-wise error rate or your false discovery rate needs to be held constant. So that was a quick review of the two activities. I'm sorry that I mistimed that, but I do hope you found it helpful nonetheless, and I will see you in class.